All right, so welcome back to another fun-filled day of differential equations. Um, how we doing? How's the homework? Any questions about the variation of parameters? How'd that go?
It went pretty good, I felt. One of the it was much easier to use the system version instead of just trying to solve for the individual variables. Um, I know it's basically the same process, but you could just plug that into the matrix and it pops out what you need. So, uh,
True, and what you're going to find though is as we get bigger, so higher order,
yeah,
um, it turns out variation of parameters, you only have to end up worrying about like the last term in that matrix multiplication. So it definitely gets faster, I think, when they're bigger. Um, but good. Hopefully, it went pretty straightforward because it's not that big of a deal. I mean, you do the process once, right? We develop it, and then it's just a matter of doing it to whatever our function is, our equation is. All right, so it sounds like we're good. We don't need to look at homeworks. All right, cool. Well, then we're going to keep talking physics. So last time we got to the point where we were looking at the spring mass system allowing for drag and saw that the solutions to those, no big deal. But I want to talk more about what happens when we have a forcing function. So let me go to the board. All right. So let's just kind of refresh our memory where we were last time. So when we had a mass that was hanging off of the spring and there was some sort of a drag allowed, we ended up having this differential equation. We had my double prime plus gamma times y prime plus k times y. And this then we're going to allow to equal some function. So we'll call it, say, big F of t. So let me just remind you what all the different pieces were. So the m, this was the mass of the object. So I'm going to put this, the mass on the spring. The gamma, this is the drag coefficient. And then k was the spring constant. And this guy f, we call this the forcing function. So everything but the big F is really a property of the spring and mass and the fluid that we're in, right? So those are all just set up for, or all come from the setup, whatever kind of situation we're in. And then we got the F of t. So we spent most of our time last time, or we got to the point last time where we, excuse me, we're solving the homogeneous form where it wasn't being forced. And we saw that there were three possibilities, again, all depending upon the m, gamma, and k. And so we could get complex numbers, which then would lead to a sinusoidal, so an oscillation. It usually had some sort of a decreasing exponential amplitude. But we also saw that we could just have exponentials, or the linear and the exponential, and it all came from looking at gamma, m, and k. And so the important quantity was gamma squared minus 4mk. And it was this number that really determined what happened. So if it was equal to 0, we say that that's critically damped. If it was greater than 0, it's overdamped. And if it's less than 0, it's just regular old damped motion. But it was all about this number right here. And so when we have something that is oscillating, we do get the oscillation. It's just a decreasing amplitude oscillation. We're in the situation where this is negative, leads to the complex roots, which then gives us sine and cosine. Okay, so that's where we were last time. And we did an example. We actually found using the initial conditions, we found the C1 and the C2, and we did all that good stuff. Okay, so now let's start talking about what happens when we have some sort of a force applied. And that forcing function, that's just going to be a force that's caused by something else that's going to be applied. And so in general, notice that it doesn't really change much. Because what are we going to do differently now if we're given a force and function?
It will be, so it will be our solution to the homogeneous plus some other particular solution,
Yeah,
which will depend on what
that's
the
exactly
function
it. There's
is.
just going to be one more step, right? We're going to still
Basically.
have to find the homogeneous solution. And then we have to find a particular solution that we can find through any of the various methods that we've already established, right? So undetermined coefficients, variation of parameters, reduction of order, yada, yada, yada. Okay, well, here's really where we have to be concerned. And that's in the situation where this forcing function has something to do with the fundamental set. That's going to be the part that's of interest, right? Because think about how these work. We're going to have our y now. I'm going to write here y sub h. I think I've done this before for the homogeneous. And then plus y sub p. So this will be whatever the solution was to the homogeneous. That's got our fundamental set. And then the y sub p, that's going to be a particular solution that goes with the forcing function. And I want you to think about what these are going to do. So let's kind of go to the different situations for the homogeneous, right? We saw the y sub h is going to take one of three different forms. It's either going to be e to the r1t, I put c1 and c2 here, and then e to the r2t, where both r1 and r2 are negative, or we're going to get that it's c1 e to the rt plus c2 t e to the rt. So that'd be the case where that this gamma squared minus 4mk was equal to 0. Or lastly, we could have y sub h equals e to the at times c1 cosine of bt plus c2 sine of bt. And let's just look at what happens to each one of those as time goes on. And in each of these, we saw that as time goes on, these are going to drop down to 0, right? Because R1 and R2 being negative, we have two negative exponential functions, so decreasing function. In this second case, again, R is negative, so that will also drop to 0. This third one, though, there's one case where it won't drop to 0. What is that situation? When does the oscillating part not drop to 0?
Isn't that when the exponential chunk doesn't exist?
Yeah, it's where this A or alpha is equal to 0. And that's the situation that we get when there's no drag. So it's not a real world consideration, except for in a situation where maybe we're doing this in a place where there's no atmosphere or something. Like if we've got something that's truly harmonic motion, like a spring system out in space, then it would definitely look like that. Okay, but regardless, all of these are eventually going to go away with the exception of the undamped motion. And in the undamped motion, well, we're going to get what we get. Okay, so some terminology that we use here is we talk about a transient bit and a steady state bit. And so here's how I like to think about these. Is that steady state, this is your long term, where we're going to be eventually. And that's what the YP is. This is going to be your long-term state. So we'll call that steady state. And then this YH, well, yeah, this affects the solution. It's just temporary because eventually T's get big enough that we don't even care anymore. And so this part, we call this, well, this is temporary. And so this is our transient state. So anytime we solve one of these things, we're going to get these two pieces. I know that we kind of get really into this homogeneous part. That's where we spend most of our time. But in an applied scenario, that part's going to go away. Like think about that spring. I gave that spring when I showed you, I pulled it down and we let it go and you saw it bouncing, bouncing, bouncing. But eventually it's going to stop moving. And so long term, without anything else affecting it, the steady state for that would be 0. And the transient state was actually as it was bouncing. Now, it's usually the transient state that is the interesting part, because you think about that spring mass system when I showed you that example. We don't care about the long-term steady state. That's not exciting. That's just a spring sitting there, right? But if we're really looking at this as time goes on, we don't care about that early bit. So most of what happens, especially again long term, it's all about Y particular. What about that piece? What are we going to get from that? And notice that that's really dependent upon big F. Like how are we forcing this thing? Okay, so the long-term status is going to be dependent upon that forcing function. So let's do one. Let's just kind of remind ourselves, work through the steps, and then we'll talk about some of the things that can happen with that big F, like with different forms, what will happen. All right, so let me just give you one. Let's just say that we've got a 1 kilogram mass. It's hanging from a spring. And I'm just going to tell you what K is equal to. Okay, so let's just say that K is equal to 5 force. So I'm not going to make you actually find it, but we saw that we can find it if we know any kind of a force and how far that force causes the spring to deform, right? And let's say we also know that gamma is equal to 1. This is another one that we know we could calculate if I just told you how much drag, what kind of force we had for a given speed, then we could find gamma. But I'm not up for wasting our time today. You guys already know how to do that. So let's just put these things in. But let's add a force. Okay, so we've got this set up, but we're also going to have a force of, let's say, 3 cosine of t. So that means that there's a force being applied to this system. That's 3 cosine t. So this is a periodic force. And that could be something just as simple as, well, physically just, okay, we're going to do this on the end, right? You wouldn't see this so much with a spring system, but later today when I show you circuits, we routinely have forcing functions that are trigonometric, because that would be alternating current, right? So if we had a circuit plugged into AC, then we'd have this kind of function. All right, well, let's just solve this and see how this goes. So we'll go ahead and put all the numbers into their respective places. So we're going to get y double prime, that was 1 kilogram mass, plus y, gamma was 1, plus 5 force, sorry, y prime, plus 5 force y, that was our k value, equals 3 cosine of t. So this will be easy enough to solve. Let's start with the homogeneous. So basically we need to figure out what r is. So let's make our polynomial. So we're going to have r squared plus r plus 5 force is equal to 0. This one does not factor. You'd need to use the quadratic formula. But I'm just going to help us out. We're going to get r is equal to minus 1/2 plus or minus I. So we're in a situation where we have complex roots. So then that tells us that the transient solution, so this homogeneous bit, it's going to equal e to the minus 1/2 t times c1 cosine of t plus c2 sine of t. All right, so cool. We've got our homogeneous. So now the question is, how do you want to find our particular? Because we have a bunch of different methods. What do you want to do?
Well, since it's in the form 3 cosine t, couldn't we make a guess that it's a cosine plus b sine and plug that in and try and solve?
Okay, so I like that. This is a nice form. This is one where undetermined coefficients is definitely a possibility. If you're there where you've got undetermined coefficients that might work, go with it. Pick that over variation of parameters. All right, but remember, we do have to worry about our homogeneous form. Do we have cosine t as one of our fundamental set?
We wouldn't because of the exponential that's tagged onto it.
Yeah, the cosine t does show up, but remember the function is actually e to the minus 1/2 t times cosine. So this is one where we wouldn't have to do anything extra for that. So we could just go with our particular as our guess being a cosine t plus b sine of t. Remember, when you have either cosine or sine, you need to have both of them as your potential. Okay, so again, you know what to do here. You would take the derivative, you would take the second derivative, you would plug it into their respective pieces of this differential equation. you would group the coefficients, blah, blah, blah. I'm gonna, again, save us some time because I know you guys know how to do this. This is gonna give us a particular solution of 12/17 cosine of t plus 48/17 sine of t. So again, lots of steps that I'm not including here. So let's look at what this would be then. If we put this all together, we would then have y is equal to these two added. So we would get e to the minus 1/2 t c1 cosine plus c2 sine plus 12/17 cosine plus 48/17 sine. And all that would be left in a problem like this would be where we go ahead and find C1 and C2. And we would need an initial condition to do so. Right? So if you were given an initial condition, you would find your C1 and C2. So let me just say that we get some numbers for C1 and C2. All right, so let's just say, suppose the initial values give y equals e to the minus 1/2 t times cosine of t minus 2 sine t plus yada, yada, yada. Okay, so I'm completely making those up, but there are going to be some initial conditions that would do that, right? But let's just say that we got here. So again, let's kind of look at this in terms of what happens short-term, long-term, and so on. So you can see why this part is transient. Because as time goes on, that e to the minus 1/2 t is going to get really small. So this cosine and sine bit is going to kind of disappear. And it totally doesn't matter what C1 and C2 are. Right? The fact that I've got in here 1 and minus 2, it doesn't matter. It could be 3/8 and minus 17/4 or whatever. That's still going to drop away as time goes on. So this would be some sort of an oscillation that decreases as we go. All right, well, let's look at this piece then, because this piece never goes away. So what do you get when you take a sine and a cosine and you add them together? You guys remember from like waves? I mean, this is in essence a wave added to another wave. You remember what you get in physics? It ends up, it's just another wave. So what we're going to see long term is just a wave. So think about it though. Think about what we were doing. We were taking the spring mass system and we were applying a force that was oscillating. Well, if I take that force and I'm just doing this, I'm grabbing that mass and I'm doing this. If the other part drops off, the bit that's actually due to the spring motion, then yeah, of course, we should end up with something that looks pretty much like a wave, because that's what we're doing at the beginning. So if you were to actually draw a graph of this, like if you were to plot this, say on Desmos, you would see, if you compare that to the steady state, you'd see that at the beginning, they're off. They're not going to look the same at the start. But pretty quickly, you're not going to be able to notice the difference between those two because this thing drops so fast. right? Like think about it. Even when you get to like t equals 8, let's say, now you've got e to the minus 4. E to the 4th, that's on the order of like 75 or something. So you're going to have 1/75 of this. It's falling fast. And that was only at t equals 8. Imagine we're at t equals 1024 or something like that. Right? So this is what you're going to see when you throw on some sort of a forced, some sort of a forcing function, is that this vibration is going to break into two pieces. There's going to be your transient piece and then your long-term steady state piece. And they're going to come from their respective spots, either from the solution to the homogeneous, right? And this came from the homogeneous because the temporary is all about the system itself, as opposed to the long term is all about the function, the force function that we're applying. All right, so yay. But let's say we had the exact same situation here, but the forcing function was slightly different. What if in this case, our forcing function had been, so let's say we had the y double prime plus y prime plus 5 force y. But what if this was now equal to 3 e to the minus 1/2 t cosine of t? So what happens now?
Wouldn't that be where a case where we'd have to tack on an extra variable because it's identical to one of the pieces from the homogeneous?
Yeah. So that's exactly what's going to happen, is that in this situation now, we're going to have to change our function so that our guess now has some t's attached. And so we're going to get those as well. And so we can get a completely different form to our steady state. So small changes there are going to lead to issues in terms of what our, or maybe not issues, but at least changes in our steady state. Okay, but here's where weird things can happen. All right, so let me change this a little bit because I don't want to go into this with the e to the negative bit. But let's just go with, again, equaling cosine. But this time, let's say that our differential equation is y double prime plus 1/8 y prime plus y. And again, we'll make it equal 3 cosine of t. And I'm even going to give you some initial conditions. Let's say that we know that initially we're going to move it by 2. And then we're going to start it from rest. So basically, I'm pulling that spring down to, well, I guess in this case, 2 meters, and letting it go and see what happens. All right, so let's see what happens with this thing. So let's get our solutions. So we make our polynomial r squared plus 1/8 r plus 1 equals 0. So we're going to get r is equal to negative 1/8 plus or minus the square root of 1/64 minus 4 all over 2a, so over 2. And if we go ahead and figure out those roots. You do see that they are going to be complex, right? Because this is going to be very negative. We got minus 1/8 plus or minus the square root of negative 255 over 64. And I'm going to go ahead and reduce that, pull out the 8, and then divide by 2. So we get minus 1/16 plus the square root of 255 over 16 times I. Okay, so that's what our R's look like. And so if we were to plot this, actually find our solution. Well, let's go all the way because I want to actually see what the solution looks like. All right, so there's our R's. Now, this thing actually, or the solution to the steady state is going to be some combinations of the 3 cosine and 3 sine, or cosine and sine of t. And if you look at that, what we see is that that combination can be put together. Let me actually show you this. Let me show you this. We'll take a real quick side step. Apologize. But remember these R values. In general, if you have something of this form, A times cosine of omega t plus B sine of omega t, if you add those together, you can think of this as a single trig function. So R cosine of omega t minus some delta, where delta is going to be a phase shift. You can actually go through the process and find out what these different things are equal to. So for example, that R is going to equal well, let's do this. So we've got, this is going to equal some sort of F naught cosine of omega t, right? So F naught is our target number. The new amplitude, once you actually calculate everything, that R is going to equal F naught over the square root of, and don't worry too much about this, like write it down, but don't stress about where it comes from because it's pretty gnarly. So this is what the new amplitude of that thing is. The M and the gamma, those are the M and the gamma that come from your mass spring system. Okay, so those are part of the system. The omega, again, that's just whatever the forcing function is. But then this omega naught, the thing about this is that comes from the original spring system, and it's K over M. And I don't remember if this was your class or my physics class, because in physics we're talking about the same thing right now. This is what we call the natural frequency. Did I share that with you guys? So this omega naught, it's the natural frequency of the system. So if I didn't share that with you, now you got it. So it's the natural frequency of the system, again, based solely on values from the system. So if there were no dampening, that's what this means. So the natural frequency, this would be with no dampening. So basically, it would be the frequency that this system would want to take on and would have happen if it weren't for dampening. So think about maybe not a spring mass system. I think a pendulum makes a little more sense. You really model pendulums the same way, excuse me. But pendulum's going to want to go back and forth, right? It's going to keep going back and forth. And in the absence of any kind of drag, it's very predictable. And that would be its natural frequency. Same thing, if we've got a spring and a mass, it's going to want to just go a certain way, right? And that omega naught is its natural frequency. The delta, the phase shift, I could show you how we calculate delta. It's a tangent kind of thing, but don't worry so much about the delta, because delta is just going to shift us. And really what I want to look at is just what's happening with this thing as time goes on. Okay, well, notice that this amplitude is dependent upon whatever our forcing function is. Because omega, that's our oscillating frequency of our forcing function. And so I want you just to look at this, and let's look and see what happens to this depending on our forcing function. So first of all, the F naught, yeah, if we've got a stronger amplitude forcing function, we're going to get a bigger amplitude. Duh. Okay, that I don't really care about. But let's look at what happens with the omega. Okay, so look at this square root. And I want you to notice what happens when omega starts really small. Let's say that omega is basically 0. Obviously, it can't be equal to 0. I mean, I guess it could, but then we've just got like a constant force of F naught, right? If it's actually equal to 0, then we would get the square root of m squared omega squared, or omega to the 4th, which gives us m omega squared. And we know what the amplitude is, but it's bad enough. But watch what happens as omega gets closer to omega naught. Right. If we start kind of fiddling with this, let me rewrite this form. Let's look at this square root bit. Ignore the F naught. But let's divide everything by omega naught squared, just so that we can kind of get it all to look like what we want. So we have 1 over the square root of m squared times 1 minus omega over omega naught squared. But what I really have to do is divide that omega naught squared into the next piece as well. So we're going to get plus gamma squared times omega over omega naught squared. And then technically, since I divided by omega naught squared, I need to multiply by omega naught squared, right? Which would be, there needs to be an omega naught out here. But omega naught, we already know what that equals. That's a k times k over m kind of deal, but let's just leave it out there for right now. So in essence, I just factored out an omega naught squared. All right, so again, when omega naught, or when omega is small, 0, 0, so we just get the m and everything is fine. But now look at what happens as omega gets closer to omega naught. If we start doing that, notice what happens is we end up getting this, this piece goes to 0. We're left with this gamma squared. And if you go back and you look at what gamma equals and how it's, excuse me, related to everything, what we end up seeing is that there is a maximum amplitude that we can get. So again, algebra. So I'm just going to put here, do algebra. If you want to see it, come find me sometime in the virtual office hour, and we'll work it out. But if you do some algebra, what you end up finding is that this R, there's a maximum value for it. I'm going to put here R max. And what it looks like is F naught over gamma omega naught times the square root of 1 minus gamma squared over 4mk. All right, now we're going to do like the ultimate trick in the mathematician's book, which is, let's approximate this. And let's use power series, because we've got something raised to the 1/2 power. So you may remember there's the binomial power series. I'm not saying that you remember what it looks like. Just remember that it exists. And what we can do then is just take the first term or couple terms. So if you do that, we're going to say then that this R max is approximately equal to F naught over gamma Y naught, or gamma omega naught. That part is still the same. But from the power series, we get 1 plus gamma squared over 8mk. And this is especially good if gamma is small, because then like the next term of the power series is going to have a gamma to the 4th. The next one's going to have gamma to the 6th, gamma to the 8th, and so on. And so if gamma is small, then gamma to the 4th is small. It's even really small, right? And so then you can kind of ignore them. All right, but what I want to do is I want to look at this and look at this in terms of what's going on with the gammas and all that. So think about critical dampening. Remember where critical dampening was? It's where gamma squared was equal to 4mk, right? So with critical dampening, you can actually pull that out of this thing. That gamma over 4mk is going to equal 1, and it simplifies down even further. But really, let's think about this. With small gamma, what's driving everything is this, right? Your maximum amplitude is going to be F naught over gamma omega naught. So when omega is near omega naught, you get huge amplitudes. All right, so the moral of the story here with this math is that huge amplitudes happen when omega is near omega naught. So omega is the frequency of our forcing function. Omega naught is the natural frequency of the system. And so when those are close, we get huge amplitude. Amplitude builds. And this is what we call resonance. So if you remember this from physics, examples of this would be taking your finger and just kind of going around a glass on the top. And if you go at just the right speed, the glass starts to sing. And that's because your frequency of rotating, your forcing frequency omega, gets to be very close to the omega naught of the glass. And it actually causes the sides of the glass to start vibrating. And it's that vibration that then is the sound that you hear. Right? Or the classic Tacoma Narrows Bridge, right? That bridge that just started kind of going like this and then got really bad. As the wind was blowing such that the forcing function was right along the natural frequency. So these forced oscillations can get into really crazy situations. And what will happen is that your solution is such that the amplitude just keeps increasing. And so instead of seeing them drop down, like in the free oscillations, we saw that it always dropped down to 0. What you can get in a forced oscillation is actually something like this. So if the forcing function is such that we get resonance happening, you'll get a function that oscillates but increases in amplitude. And in an applied situation, what that means is that the forces usually get too big and overcome the structural integrity of the material. That's why eventually that wine glass will break if you keep vibrating it at the right frequency. Why that bridge fell down. For those of you that are going to be like civil engineers, structural engineers, you got to worry about this with buildings, right? There's a story of bridges that have fallen because soldiers have marched across them at just the wrong pace. I don't know if any of those are actually true, right? But mathematically and physically, they definitely could. Anyway. The other thing that I do want to mention, though, is that when they're not the same, when these frequencies are not the same, that's when you can get beats. And I don't know if you remember that from physics, but when your frequencies are off by a little bit, you can actually hear the pulsating, that's the beats. Musicians use this a lot for tuning instruments. You know you're in tune if those beats go away. But anyway, so that's what happens when you got forced oscillations. All right, but enough about springs. Let me show you how this exact same scenario in terms of the second order differential equations shows up when we're talking circuits. So we're going to make a circuit here that's pretty basic. And what we're going to have in it is a resistor. We'll have a capacitor. And we'll have an inductor. And of course, we'll leave ourselves a little space for a switch. So for those of you who don't really know your circuits very well, that's okay. Just sort of go along for the ride here with me. So this is a capacitor. And a capacitor stores charge. Okay, so kind of think of it like it's a battery. What it'll do is it collects charge until the charge is enough that it allows the charge to go from one side to the next. So it's kind of like a delay. For example, intermittent wipers on your car, you know, those ones that just go every once in a while. It's usually a capacitor that they use to drive that. It's a set amount of time till that capacitor fills and then it goes. So that's a capacitor. And the one up top, this is a resistor. And resistors are anything that basically use your energy. So when you plug your toaster into the wall so you can get your toast in the morning and it turns on, those coils are resistors, the coils that heat up. So anything that actually uses the electricity, that's a resistor. This little curvy guy, this is an inductor. And an inductor is something that will induce a charge in something else. So for example, if you've got a rechargeable toothbrush, like an electric toothbrush, those usually use induction. So they don't actually have to be plugged in, they just have to be sitting on the little knob, right? And so that's an inductor. And then this guy's a switch, just gonna turn it on and off. All right, so what'll happen if the switch is open, nothing's going on. When we close that switch, because there's got to be some sort of a power supply. Let me put a power supply on here. Okay, so there's your, we call it EMF. So it's a battery or wall socket or something. But anyway, so as soon as we close that switch, a current is going to start and it's going to flow this way. All right, so this is what we call an RLC circuit. And what this stands for, the R is for your resistor, because resistance we measure with R. The L, that's your inductor, because the inductance is measured in L, or we use the letter L for that. And then C is for your capacitor. Okay, so if you ever see something in a book and it says RLC circuit, that's what we're talking about. It's got all of them. Okay, so in terms of the units and everything, don't worry too much about that. It's capacitors are, let's see, resistors are ohms, inductors are henries, and capacitance is
Farads.
farads. Thank you. They're all named for their respective quote unquote inventors or whatever. Okay, so here's our good old RLC. Now, when it comes to looking at the energy in a circuit, we look at voltage. Voltage is potential. And so we're going to look at the potential energy, and specifically the potential energy drops as we go across these different things. So I know for some of you, it's been a long time since you've seen this. For some of you, you haven't seen it. So let me just sort of give you all the different things. When we go over a resistor, the change in our potential energy, so the change in our voltage, so let's do this for the different component. We'll make a little chart here. So we got our component and then the voltage drop. So for a resistor, the voltage drop is actually equal to I times R, where I is your current. Okay, so again, in case it's been a while, that's actually the current. That's how much charge is flowing over time. So that's I times R. All right, so that's what happens over a resistor. A capacitor its voltage drop is equal to Q over C. Again, C is the capacitance of the capacitor, and Q is charge. All right, now I seem to recall that when I brought this up before, you guys mentioned that you didn't really do anything with inductors back in physics, so you may not really know how this plays out.
I mean,
But
we did.
yeah,
Yeah, we did.
okay. So do you remember what it is over an inductor?
I don't recall because I don't use inductors.
Okay, so it's the henries, it's whatever the inductance is, times di dt. So it's the change in current with time. All right, so that's the voltage drop that we get over the respective pieces. So if we use Kirchhoff's law and kind of just go over this circuit, since we've just got one loop, basically this is how it plays out. We've got our voltage drop over the resistor. Like I said, capacitor first. So that was Q over C. Then we're going to get the voltage drop over the resistor, which was I times R. And then we're going to get the voltage drop over the inductor. I'm going to write it as L times I prime. And all of that is going to equal whatever our electromotive force is. So I'm going to write equals EMF. So again, that's our battery or the electrical outlet or whatever's providing, it's forcing the current. Okay, so you're starting to look at this and see, oh yeah, this is starting to look a little bit like a differential equation. We got an I prime, we got an I, but then we got that term with Q. Well, here's where we have to remember one other thing. Anybody remember the relationship between charge and current?
Isn't current the amount of charge per time, right?
It is. So current, I, is actually equal to Q prime. It's the change in current with time. All right, so notice what happens. If we replace all those I's, this thing turns into a second order linear differential equation with constant coefficients. And I'm going to change this. I'm going to write that as E of t, E for electromotive force, but t because it's time dependent. All right, so check it out. This is exactly the same form as our spring mass system, right? Spring mass system, it was an M here, a gamma, and a K. But it turns out that mathematically, a circuit is identical to a spring mass system. Crazy. Completely crazy, because they seem like they're completely different processes. And they are. I mean, they're completely different processes. But we get ourselves another second order linear with constant coefficients, which means we know exactly how to solve. And it also means we know exactly what's going to happen with our solutions, right? In terms of the homogeneous, we're either going to get a we're going to get an oscillating and potentially a decreasing oscillating, right? Then, or we could get something that's exponential but with negative exponential, because again, all these numbers are positive. Inductance, resistance, and capacitance are all the same. And so then in terms of initial conditions, right, if we're going to have some sort of T naught, well, we can have whatever our starting charge is. So this would be like the charge that's built up on the capacitor. And then our derivative, Q prime, that's actually going to be our initial current. So if you know the initial charge and the initial current, those are your initial conditions in this case. So in the spring mass system, we did have to know, what is the initial velocity and the initial position. But here it's just a question of, do you know the initial charge and the initial current? Because if you've got those, then you're good. All right, so again, this is all going to be dependent on our EMF. And depending upon what kind of system you have, your EMF will take different forms. When you plug it into a wall, alternating current, that thing is sinusoidal. If you use a battery, it's not. In fact, theoretically, a battery is constant forcing function, right? It's 9 volts equals 9 or equals 12. In reality, those die out with time. So you would have to take that into account. But when it comes to actually solving these things, it's no different. So let's set one up. Let me give you some actual numbers here, and we'll see if we can get it set up. I don't know how far we'll go with it, but I want you just to at least see how we're going to get it set up, because once it's set up, you know what to do. All right, so for example, let's say that we've got a circuit and we're going to have resistance of 3 times 10 to the second ohms. Ohms are omegas, so just so you're familiar when you run into that, if you see it in a problem. We're going to have a capacitance of, let's say, 10 to the minus 5 farads, and an induction of 0.2 henries. Let me go ahead and give you an initial condition as well. Let's say that initially, no current, and there is a charge of 10 to the minus 6 coulombs. And we're going to go ahead and see if we can figure out, well, A, we're going to build the differential equation, and then let's see what we end up getting. Now for this one, let's assume that there is no EMF. So this capacitor has already been charged by, whatever process. But now we throw the switch closed and we see what happens. All right, so let's start by building this thing. So we need to know L. Well, L is 0.2H, so we're going to get 0.2 times Q double prime. And then we get plus R times Q prime, so plus 300 Q prime. And then we get plus 1 over C, so 1 over 10 to the minus 5 times Q. And that's going to equal 0. So let's just divide everything by 0.2, make life a little bit easier for us. So if we divide by 0.2, that's the same as multiplying by 5. That's going to give us 1500 here for Q prime. And then we're going to get plus 50,000 times Q equals 0. Nope, not 50,000. How about 500,000? So let's at least go as far as figuring out what the fundamental set is. So my first question is, well, let's just do it. So here's our R. So R squared plus 1500R plus 500,000 equals 0. So my question here is, what are those roots? Are they positive? Are they negative? Right? Are they complex? Are they repeated? Well, this factors. It's R plus 1000 times R plus 500. So what we're going to get for our fundamental set, or what our solution is going to look like, is Q equals C1 times e to the minus 1000t plus C2 e to the minus 500t. You know what? We'll go the whole way. Let's get all of our numbers. All right, so we know that initially there's no current, but there is this charge. Okay, so at time equals 0, we get C1 plus C2. And so we get C1 plus C2 is going to equal 10 to the minus 6. When we take a derivative, we're going to get minus 1,000 of these. So minus 1,000 C1. We're going to get minus 500 C2. And again, when we plug in 0, that needs to equal 0. So that equals 0. Well, we're so close, we might as well just go ahead and get this. If we multiply by 500 to get rid of the C2s, we get minus 500 C1 equals 500 times 10 to the minus 6. So C1 is going to equal negative 10 to the minus 6, which then means C2 is going to be 2 times that. So that when they get added together, we get what we need. So there's our C1 and our C2. So when all is said and done, here's our formula for the charge. So this would be the charge on the capacitor. It's going to be minus 10 to the 6 times, no, here's what we're going to do. Let's keep the 10 to the 6 as a factored out. So we're going to get minus e to the minus 1000t plus 2 e to the minus 500t times 10 to the minus 6. So check out what happens with this one. As time goes on, these are going to drop off. So eventually what we're going to see is that the charge on the capacitor drops to 0. And that should make total sense. Because if we have no electromotive force, if we're not attaching this to a battery, then the charge needs to dissipate because it's going to leave the capacitor, it's going to go through the resistor, the inductor, it's going to be used, and eventually it's all going to get used up. What if I ask for the current? What would you have to do to figure out the current on this thing?
Wouldn't you just have to integrate that function?
Yeah. So it's actually the other way around. I
Oh,
is Q prime.
yeah.
So we would differentiate this. But if you differentiate this, then you would get your current as time goes on. But you'd see the same thing, that current's eventually going to drop to 0, which it should, because we're using up all the energy. Anyway, so the moral of the story here is RLC circuits are no different than springs on masses on springs. They do exactly the same.
Okay, so there's a little bit of why we care about these. Like, what the heck is the point? The point is, in lots of applications, second order differential equations come up. All right, so there's chapter 6 in a nutshell. It's really just applications. And I know that this has probably been really boring, because I know for me it's really boring, because once you've learned how to solve them, okay, right? The hard part, legit, the hard part is figuring out what numbers you put where. And even that is not that difficult when you're told, oh, hey, the capacitance here is blah, or the resistor. Now, in the real world, where this gets difficult is you have more than one resistor. You have more than one capacitor and all that. And so if you guys remember your rules for things like resistors in parallel versus series and all that, it's kind of the same idea. You try to reduce it down so that you have one resistor. And that was kind of the point of those exercises back in physics. You may have wondered, why do we care about that? But basically, it makes it so that you can treat it as one resistor, one capacitor, one inductor, so that you can fire it into this and call it good. All right. So anyway, it is what it is. It's just applications. So I think I'm going to stop here. I know that we've got technically like 15 more minutes, but I think we're probably good. So any last questions before I stop the recording here?